Hi, welcome to the second lecture of the course Advanced Techniques for Mobile Sensing and Robotics, which is part of the Master of Science Geodetic Engineering. This is an overview of the course, and we are here now in the second lecture, as I just said, and it's about trajectory estimation. As a reminder for the motivation, what we are talking about here in this lecture mainly is how to do mobile mapping in the sense of a sensor system with multiple sensors moving through an environment, and while it's moving, it's generating measurements, and these measurements should be consistently referenced in a global coordinate system. And what we need to do is transform all these local measurements of sensors into some sort of global coordinate system in order to generate a spatial information about the environment. So this is what we motivated last week, and we will continue now with this. In the last chapter, the last lecture, we explicitly derived the georeferencing equation, which creates coordinates of objects that are observed in the local sensor coordinate system. In this example, it was for mobile laser scanning. So we measure with our mobile scanner, which is moving through the environment. We measure objects because the object reflects the laser light, and there's a distance and an angle measurements to that object. And then we have a chain of transformations which are necessary to generate the global coordinates of that measurement of the laser scanner. It involved a calibration part and involved a trajectory estimation part, and we today speak about the trajectory part. I explained last week how these data correspond to the coordinate systems that are involved here. So this R here is the orientation of the vehicle, right? It's a transformation between the body system or the vehicle system and the navigation system, and it's based on these three angles here, right? So these are the Euler angles. They are here defined. They show how the vehicle is oriented with respect to the navigation frame. The navigation frame is a frame which is tangential to the ellipsoid representing the Earth, and here it's the x-axis is pointing east, the y-axis is pointing north, and the z-axis is pointing up. And these coordinates here basically are the vector to the mean of to the center of the body system, and these two here are basically just a reformulation of those vector here in geodetic coordinates, and you can see them here down here, and they are necessary to transform the navigation system to the global Earth system. Okay, so these are all parameters which are changing over time because they describe the position and orientation of the vehicle with respect to the Earth. And the question is now, how can we derive these parameters? This has been extensively explained in the last semester, where we talked about like sensors and state estimation lecture, where we talked about how to generate this using what kind of sensors. And what I want to do now is I want to repeat those findings and those techniques and discuss them a bit more with respect to accuracy, and also introduce a method how to improve this estimation process. Okay, last semester we talked about different sensors that are involved in those mobile mapping systems, and there were many mapping sensors, like the sensors which are actually used to observe the environment, like laser scanners and cameras. So we will not talk about them today. And then we are interested in navigation sensors, and the navigation sensors that we used and that we've seen already last semester are inertial sensors, odometers as relative sensors, and GNSS, mainly GNSS, as absolute sensors. We can use the mapping sensors also for generating trajectories, as it is, for example, done in SLAM algorithms or other similar things where we use the actual observation sensors to generate information about the motion. But again, this is also something which we will not talk about today. We focus on the combination of inertial sensors and GNSS to generate a high precision orientation and position information. When we talk about inertial sensors, what we will do in a second when we repeat what they actually measure, we need to talk about the inertial frame, because inertial sensors measure their information with respect to the inertial frame. The inertial frame is the coordinate frame which is fixed with respect to the rest of the universe. So in this Earth frame, which is marked with the E here, which is attached to the Earth, this is the frame which we are interested in, right? This is the frame which contains global coordinates which tell us exactly where on Earth we are. For the inertial sensors, we need this inertial frame. The inertial frame, the axes are fixed to the rest of the universe. There is a convention how this is done, and the X and Y axis are somehow fixed, and the Z axis is the same axis as the Earth system. So that's a convention, and the origin of that inertial frame is also the same origin as the Earth frame. So that means the difference between Earth and inertial frame is that the inertial frame rotates around the Z-axis, the Earth frame rotates around the x-axis with the Earth's rotational rate. So there are two types of inertial sensors, accelerometers and gyroscope, and we start with accelerometer. The accelerometer is measuring the specific force of a body with respect to the inertial system, and the specific force is the non-gravitational acceleration. What we see here is a working principle of the sensor. So usually it's a proof mass which is fixed between two springs, and as soon as there is an accelerating force applied to that system, to that sensor, the proof mass inside is moved toward that direction. The acceleration is toward that direction, right? And this displacement here is proportional to the accelerating force because of Hooke's law. And then this displacement is measured and can be used. It's proportional to the actual force. Okay, so the specific force of the body relative to the inertial frame given in body frame coordinates. This is what we get from an accelerometer, right? This is the specific force of the body frame with respect to the inertial frame given in coordinates of the body frame. And what it means, it has the actual acceleration minus the gravitational acceleration. So why is this the case? So we can probably have an example here. So if a sensor is falling down, we just leave it, let it fall down from whatever, from a tower, and it falls down to the earth. While it's falling, it's measuring 0, right? If we But if we want to look at the acceleration, it's actually accelerating. It's becoming faster and faster and faster and faster. So it's going down with 9 point. So this is the acceleration that it is having with respect to a motion, and because it's measuring 0, and this is a gravitational part of it, right? So this is the gravitational part, which we have to subtract, right? So we have, if we measure 0 and we want to know how fast it is actually moving, and we want to recreate the trajectory, what we have to do is we subtract g in order to get the acceleration. A gyroscope measures the angular rate of the body relative to the inertial frame given in body frame coordinates. Again, this is this notation that we've seen before. Relative size of this body frame with respect to the inertial frame given in coordinates of the body frame. This is what the angular rate sensor gives you. We had two different types of sensors. One was MEMS devices, which can be built very small and cheap, which are not so accurate, and then the more accurate devices, which are based on the Sagnac effect, such as fiber optic gyros or ring laser gyros, that are used in more expensive systems. The question is now what to do with those sensors, and there's an algorithm that we talked about intensively last semester. It's called the strap-down integration algorithm, and I want to repeat this algorithm now before we proceed to the rest. The strap-down integration algorithm can be formulated in different coordinate systems, and the easiest one is the formulation in the inertial frame equations. What it means is that if I use the inertial frame equations, that means that my resulting position and orientation are given with respect to the inertial frame. Of course, the inertial frame is not a coordinate frame where we're actually interested in, but it's the easiest thing because the measurements of the inertial sensor that I just said before are already with respect to that inertial frame, so that it makes the math much easier. So the inertial frame is a system, the resolving frame for position and orientation. So it's basically the results are given in the inertial frame. What we do first, we update the orientation. That means we use the angular rate sensors I just said before, like these angular rate sensors from the gyroscope, and we use the orientation at the last time step to update the attitude. Right? The inertial sensor is a relative information, so there are no absolute values involved. So the only thing that we can get is we can get the change with respect to the last state. So we have orientation at some time before, denoted as a minus here. We now have an angular rate, and then we get a new attitude or orientation update. This is done usually using this equation here. So this is the time, right? This is the time between the two states, and this here is created by those omegas, this symmetric matrix. And a new update of the orientation. This is now the orientation between the body and the inertial frame, as I just said before, because the resolving axis is the inertial frame, is given by the old orientation and some term which is proportional to the angular rate that we measured and the time that has been evolved since then. The next thing is then to transform the accelerometer measurement to the inertial frame. So the accelerometer measurements are given in the body frame because this is a resolving frame of the sensor, right? And we want to have them in the inertial frame with respect to the inertial frame. So we rotate those measurements from the accelerometer using the just updated orientation to the inertial frame. Then we need to subtract the gravity component. So in order to get the A, right, from the measurement of the specific force, we need to correct for gravity, meaning adding the gravitational part here, and this gives us the new acceleration, right? So this is here. So here we have the specific force, and then we transform it to the inertial frame, right? This is mean here, this is written here, and now we can use it to update the velocity, which is the next step here. So we use that acceleration component, that acceleration here, multiply by the delta t or tau I here, and then add it to the velocity of our last state. So this again, of course, needs the velocity from the last time step, and then we can update the velocity. Of course, here we need to subtract for the gravitational component using some sort of gravitational model. Now we have a new velocity, and the last thing is then update the position by using the old position and adding up the velocity times tau, right? So again, we have a position from the last time step, and we use this velocity here to update the position to get a new position. And this is done here. All these equations here have some approximations inside, so it involves an integration, and these are integration errors. This is the simplest integration you can do, right? This is just, there are much more sophisticated integration algorithms like Runge-Kutta methods or similar things. This is just to show the basic idea and to show how this in principle works. Okay, so that means now we know how to use inertial sensors, omega and f information, and the old time step to the old information or orientation, position and velocity to get the new values. And this is what we call strap-down integration. The example from before gave us the angles and the position with respect to the inertial frame. But as you see here, and as we've seen before a few times already, this is not what we want. What we want is these angles between the body and the navigation frame, and not the inertial frame. We want to have it between the body and the navigation frame. And then we also want to have the vector between the earth frame and the navigation or body frame. And this is the goal. This is what we want to have. And in order to do that, we need to reformulate the strap-down algorithm to work in the navigation and the earth frame. So this is what we want to have. In the ideal case, we want to have a position of the body with respect to the earth frame, given in earth frame coordinates, the velocity of the body with respect to the earth frame given in navigation frame coordinates, and this here is representing an orientation between the quaternion here, between the body and the navigation frame. So this is a vector that we are interested in, and the strap-down integration is then just a function of this vector at the last time step, and as I said before, those angular rate measurements. And if you do this in using those coordinate frame conventions, then the things become very complicated. And this is just as a reminder, this is written here, because if you consider all these different coordinate systems, then you have to consider the Earth's rate, the transport rate, and all Coriolis corrections. These come because the rotating Earth on which we are now, it has to be considered in our integration process. Yeah. So that, just as an example, if I put my angular rate sensors on a table and don't touch it, then it will measure the Earth's rotational rate. But still I want to, because this is a rate in the inertial sensor system. But with respect to the navigation frame, the orientation, the rotational rate is 0. And I have to consider all these things if I want to do the integration in the system that I'm actually interested in at the end. This just makes it more complicated. You can have a look at the last semester to repeat that, or to some books that I mentioned also in the last semester. Now that we know how to calculate or update position and orientation using inertial sensors, we can talk about an important point for strap-down integration, which is initialization and alignment. So the problem is, because we always measure and calculate a new position based on an old position, or a new orientation based on an old orientation, we need to know what the starting values are. So for position, starting values can be used by other systems like GNSS. You could use a GNSS position as a starting value and then use inertial sensors to update it. Or you know where you start, like you start from a known position. For example, the car has parked at a known position, then you can use those values as starting values. For the velocity, you can also use an external system like GNSS, or you start in a static situation, for example. Like if you start in a static situation, then you know that the velocity is 0, right? So this can help. For the orientation, starting values can be accelerometer leveling. So that is basically using an accelerometer as an inclinometer, and it gives you, if you not move while you measure, it gives you the angles between the gravity and your sensor. Or you use gyro compassing, which measures the rotational rate, and then based on the fact that you know where you are roughly on Earth, it gives you the direction with respect to north. The other option to get direction with respect to north is magnetometers. They give you a 3-dimensional or sometimes 2-dimensional vector of the Earth's magnetic field, and then you can calculate your own orientation with respect to that field. Or the last thing, which is usually done in many systems, are multiple GNSS antennas. So if I have 2 GNSS antennas, I can calculate my orientation with respect to north. The other important question is, if we do this, if we integrate angular rate and accelerometer sensors, what does the error? So how does the error behave? So what is the actual error of this procedure? And this is a very important point. If you, for example, look at the orientation update which we have here, then you see that there is this angular rate component here, and this is the delta t. And if there is an error in this angular rate component, let's say gyroscope bias, right, a constant offset of the sensor, then this, of course, will be integrated to an angle error, and this means that we have a constantly growing error in the angle, which goes with t, right? So that means, for example, a bias of 0.1 degree of the gyroscope give us an orientation error after 30 degree orientation after 5 minutes. This is a very common error in inertial sensors, especially the gyroscope bias, for example. It's usually existing. It's a bit problematic that it's changing also over time slowly, and it can also be different when you switch it on. You switch the sensor on, it has a bias, and you switch it on the next time, it has a different bias. And this can happen with, it usually happens with angular rate sensors, and so this is a very common error. You could also look at the position and velocity update, and here we have a similar behavior. If I here, for example, have a constant velocity error, right? So if my velocity is constantly wrong for whatever reason, then it's similar as with the angular rate error. Then it leads to a position error, which is proportional to the time over time. So again, 0.1 meters per square second velocity error leads to 30 meter position error after 5 minutes. This is just an example. And the other thing that we have is a constant accelerometer bias, which leads to velocity and position errors. Yes. So of course, if the accelerometer here, right, if the accelerometer has a constant error, then the velocity error grows with time, linear with time, and then the position goes with t squared, right? So this quadratically grows over time. So this is even worse. Yeah. So for example, 0.01 meters per square second accelerometer bias gives you 450 position error after 5 minutes. And this is, of course, a lot. There's another error in inertial sensors, and this is actually the most problematic one. And this is that the attitude error, if you have an error in the attitude, then this translates to an error in the position. And this is because of this part where you correct the measured specific force by the gravitational component, right? So if your gravity compensation is wrong, yeah, so if your estimated orientation is a bit different than the reality, then there's a part of this measured reaction to gravity which is considered as an acceleration, which then leading to an acceleration offset. So we can see that here this is a true specific force, right? And this is a calculated specific force, and there's an angular rate error in between, right? Then there's an offset between. This offset here then is actually coming from the gravitation, but it is assigned to an acceleration, to a translation acceleration, which leads to position change or velocity change and then a position change. So that means if I have a constant an attitude error here, yeah, like this, for example, it's a very small attitude error, 0.057 degrees attitude error. And if this is constant, then this leads to a 440 meter position error after 5 minutes. Yeah. And if you look this, if you now say that this attitude error is growing linearly over time because it comes from a constant gyroscope bias, then this gyroscope bias leads to an attitude error which goes with t to 3. Yeah, so this goes cubic with time. So the position error based on a gyro bias goes cubic with time. So, and this is very critical, right? So the wrong orientation is the most critical point in strap-down integration. Yeah. So that means that the quality of the gyroscope is actually more important than the quality of the accelerometer, because a low quality gyro leads to a very unstable and inaccurate attitude, and this leads to an accelerometer bias because of the wrong gravity compensation, because of assuming a wrong orientation, and then this goes with time very fast. So a bias of 2.1 degree per hour leads to 450 meter position error after 5 minutes. This is again showing the same things as some functions, right? So constant velocity error leads to, it goes linear over time to the position. Constant acceleration error goes quadratically with time, right? And here a constant attitude error goes quadratic over time, and with a constant angular rate error, which as I just said is a bias, for example, goes cubic with time. Yeah. So this is what's happening here to a position error. Okay. Another thing is this is so what we see before are systematic errors and how they influence the noise. And the other thing, you can also look at what noise does, right? So if you have a noisy measurement, if you look at Gaussian noise, which is projected representing the uncertainty of the sensor, and you project it to the future, looking at the uncertainty of the position based on the noise of the accelerometers, and this has also a certain time behavior, which you can see here, right? So the longer you measure, the more the uncertainty grows based on the noise of the gyro and the noise of the accelerometer. Good. What we see now is that we can use inertial sensors to calculate position and orientation, to update position orientation every time we get a new measurement, assuming that we know the starting values of position and orientation at some time. And what we also seen is that the error on the uncertainty of this estimation becomes bigger and bigger and bigger with time. And it goes quadratically or even cubic with time, depending what we look at. What we also learned last semester is how to fuse these inertial sensors with GPS observations or with other knowledge that we have about our motion, like motion models and other things. We repeat that quickly now. We learned about the linear Kalman filter, right? So if we can describe our system as a linear system and linear measurements, then this here is the new state, which can be described as some linear function of the old state. And here we have some control inputs, like also described as a transition or like a control matrix, which says how our control inputs influence the state, and this is the noise matrix, which tells us how noise actually acts on the state. And this here is the measurement. It tells us the measurement model H here. It's a linear. It's a matrix in this case, and it tells us what is the measurement if this is our state. Yeah, and of course there's some noise as well. So this was a Kalman filter, and it was described in detail. In the general case, of course, these here are not matrices. They're not linear. In the general case, the new state is a function of the old state, some noise and some control inputs, and the same holds for the measurement. So in the common model, the measurement is calculated from this state using some sort of arbitrary function and not based on a matrix. These were the equations of the Kalman filter. So the first thing was a prediction step where we generated the predicted state based on the old state plus this linear model, this linear times this linear model. The same we could do for the covariance. We predicted it to the future using this transition matrix phi and some system noise, which represents our uncertainty about that model that we have here. And then in the correction step, we calculated some gain, which depends on the predicted covariance, on the measurement model, and on the measurement noise, which we have here. And then using this Kalman gain, we updated the states. This now included the measurement that we actually have, right? And we could also update the covariance based on that Kalman gain factor here and the measurement matrix and the predicted covariance. So this was a Kalman filter algorithm assuming linear models and Gaussian distributed noise. We learned also very quickly that this assumption of the linear model does not really hold in most cases. This is now a system, an example that we talked about is if we have a position of our car, for example, here of x and y, so it's just a two-dimensional problem, and this gives us the orientation of the car with respect to north, for example, or to east. Then this model is this model says that the new state can be calculated based on the old state and a velocity measurement and an angular rate measurement around the z-axis, which we call control input, using this equation here. And here we can directly see that this is a nonlinear function. So we can't find a way of writing a matrix which maps the old state to the new state based on these control input variables. And the same a similar example we can look at for the measurement model. So this is an example for a nonlinear measurement model. So any model where I, for example, measure the distance to a known object is a nonlinear model, right? So we have the distance function here. If we square those components and then build the square root in order to get the distance between our car and, for example, a GPS satellite. If this is our measurement, right, then this is a nonlinear thing. So we can't formulate a linear matrix which is called H. Okay, and in the nonlinear case, we can build the extended Kalman filter, and this basically means that we linearize our models. So we can do that for the phi, for the transition matrix. We linearize with respect to the state, yeah, and we linearize at the point of the prediction. So we first predict using the function here. We can use a nonlinear function if we want. And then for the linearization, we use that predicted position, or alternatively, that was wrong. We use the last state here, right? Here we lose a state from the last position as a linearization point, and for the measurement matrix, we use the predicted estimate as a linearization point. Apart from this linearization, the filter is pretty similar. It's just that we have to do this Jacobians here to get the linearized matrices. Coming back to that specific model, to that specific example that we discussed, we used here. As a control input, we use the angular rate measurement, and here we used a delta S, which is a path increment that we get, for example, from an odometer. And then here, these are noise values. It's the uncertainty of the path increment, and it's the uncertainty of that gyro measurement. And if we formulate, we've seen that before, if we formulate this as a function here, then it looks like this. So these are the control inputs that we have, and these are the noises or the uncertainties that we have here in this model. We can linearize this. Yeah, this was shown before. We linearize with respect to delta x, and then this is the result. This now tells us how to calculate this part here of the model. So we said that our Q matrix, our system noise, depends on the uncertainty of the odometer and on the uncertainty of the gyroscope. This is given here, and what we have to calculate is how this uncertainty influences the covariance, and this is by calculating the derivative with respect to the noise here, and then this is the result, right? So this is telling us how to calculate this system uncertainty component, which we have to add here in the prediction of the covariance. The measurement model is rather simple. The measurement model here is just an observation of GPS in the two-dimension X and Y. So that means that we directly observe those two components of the state, right? And then the measurement model is very simple. It's just a one here and a one here. And the measurement noise is just given by the sigma squared and for X and the sigma squared for the Y coordinates of the GPS. We've seen this example in the last semester and we discussed this in detail, and you already also implemented it at least in a similar way in the two-dimensional example. I want to also repeat what that means for a three-dimensional thing, right? So because if we combine now the strap-down integration that we've seen in the beginning, integrating specific force and angular rate in 3 dimensions to get a position, if we now combine this with the Kalman filter example that we've seen before, then we are already very close to what we do usually in GPS-IMU integration problems. So we estimate the position and the orientation of the system in all dimensions, not just X, Y, and some orientation angle. We use inertial sensors and gyros, inertial sensors, so accelerometers and gyroscope as control input, right? So the system model that we assume in our filter is basically the strap-down inertial integration. So we use accelerometer and gyroscope as as control inputs, and use this strap-down inertial integration as a update step in the Kalman filter. Additionally, because accelerometer and gyroscopes have time-dependent systematic errors, for example, a bias, right? We estimate that bias as part of the state vector as well. And this is important because we've seen also that a wrong bias can quickly integrate or add up to wrong orientation, velocity, and position updates. And this is why we say, okay, we know that we have some sort of systematic error in that measurements. We then model them in the state vector, and we use GPS as measurements. We use positions that come from my GNSS receiver. If we do that, then this is called a loosely coupled integration, right? So it's a loosely coupled GPS-IMU integration. And we can even use raw GNSS data like double differences and carrier phases, all the things that we've learned in the last semester in GNSS lecture. We can also use that as observations in the filter. And in this case, this is called a tightly coupled integration. So it's a tightly coupled GPS-IMU integration. Okay, this is written as vectors. So I repeat what I just said. So the state vector then is this quaternion here representing the orientation. This is a position. This is a velocity, and these B gyro and B accelerometer are the bias values. So of the sensors. So it's 3 axes, 3 axes, 3 axes, 3 axes, and this is actually 4, but with 3 independent parameters because it's a quaternion. So 3 angles basically here. The control input are the IMU sender readings. It's specific force here, and it's the angular rate here. It is also 3 axes each, yeah, and the measurement is 3-axis observation as well, like a 3-dimensional GNSS position in this case. It's also good to look again at those indices here, saying that the orientation is given as the orientation between the body and navigation frame, and so on, because this is sometimes a bit confusing. What are actually the values in which coordinate systems are they given with respect to which other coordinate systems. So again, we've seen that before. This strap-down integration algorithm now in the context of this update function in the Kalman filter. So this here is the old state, right, which is here, and then we have the inertial sensor readings, which is here, and we have then the uncertainty of the inertial sensor readings, and the output then is this this state, this new state, which is shown here, right? So this is how we use the strap-down integration that we've seen before as part of the Kalman filter that we've also seen before. The measurement model then is again as simple as the one before. We directly observe in X, Y, and Z. So we're directly observing those three parameters here. So the matrix, the measurement matrix, is just the H that we see here with those three ones at the correct position. The measurement noise then is this. I want to remind you as well that this measurement noise here of the GPS is a bit critical, because this measurement matrix, and this is what we usually use in the Kalman filter, right? We use a measurement matrix R, which looks like this, and we usually put in some assumptions on the uncertainty for X and Y and Z axis. This is what we usually do, and it usually works. But I just want to point out again that that this is actually wrong, right? So GPS measurement or GNSS measurements are not normally distributed. This is an example of, I don't know, a few seconds of GPS data. And what you see here is a very, very systematic behavior, right? So this is in the order of a few centimeters, let's say, right? And you see this is a static antenna, not moving at all, and this is the observation that we actually see. So this is not noisy, this is not normally distributed error, it's a different thing. So GPS observations are also not, they're also time correlated. So this is why this writing an R matrix like this is actually wrong, but it's in most cases still the best thing we can do. And we account for this by making this here then a bit higher than we actually would do it. Okay, this is just to remind you of the problem of GPS noises. And okay, where are we now? Now we have talked about strap-down integration, which can be used to get position orientation based on starting values. And we seen how this information can be fused with GPS readings in order to get a non-drifting, better trajectory. So let's now look at a certain problem. So here we now have a result of our filter that we just before integrate GPS IMU integration filter, and we now come to that point here where a GPS outage starts, right? So here at that point the GPS somehow breaks and doesn't give us any information anymore. So now what happens here is what we discussed already after the strap-down integration. Our error grows and grows and grows over time, right? So this is a position error here, and it grows over time. And now at some point here, the GPS comes back to life. So that means what we have now is we have a jump or some sort of fast jump, which goes here back to brings our positional error to 0, and we can continue. Okay, so this is what happens usually, and it happens actually very often in Kalman filters, that if GPS is not good anymore, or it's gone for a while, then you have those jumps, right, where it quickly jumps back, and the time it needs to go back, to jump back, actually depends on the models, on the noise that you put in here. So this is basically, this is a tuning parameter of the filter. Yeah. So the tuning determines how fast you go back. Okay. So this is what happens, and there is something we can do about it. There is something we can do about it, about this jump, and the reason is that when we come back here, when we are at that point, we assume that we only know all the measurements up to here. So if we have a non-real-time situation, we can actually do something about it, and this is called smoothing. And this is what we will talk about next. So what is smoothing, and what is the difference between filtering and smoothing and prediction? This can be seen here. So we have some time of measurements and a time where we want to estimate our trajectory. And what we've done so far, what we do with for example, Kalman filtering is what we've seen here in the middle. Yeah. So we have, these are all the measurements. We use all the measurements up to the time k to estimate the trajectory at that time. So all measurements that we've seen so far up to the time tk are used to estimate the position and orientation at that time. There's something else which is called prediction. This means that we use some sort of measurement, some measurements, but not until the time k, right? So what we do here, we use all the measurements, for example, up to this time, and then predict the state at time tk, and this is called prediction because there is basically a lack of information of measurements here, so we predict until that point without any evidence except, for example, a system model that we have. And the last thing, and this is what we talk about now, is smoothing. And smoothing means that I estimate the pose or the state at that time using all the measurements that I have available. And these are also the measurements which appear only after that time tk. And this is, of course, something which you can't do in real time. So if you have if you want to have a real-time estimate of your, so the best estimate that you can have at the time tk, then you need to do filtering. If this is your result, you have a real-time problem to solve, for example, very often in robotics, you need to know where you are to do something, to trigger some sort of action, or to control some actuator, then you need to do filtering. Yeah. And if you don't have the problem that you need to do that in real time, you can do smoothing. For example, if I'm driving around in the city to get a very good 3D model of my city, then it's probably not necessary to calculate my trajectory in real time. So I could wait until I have all my measurements, and then I could do smoothing. So what we in the example of mobile mapping, then smoothing is the much better solution, because if we filter here, we ignore all those measurements that we already have. We ignore it and just use all the measurements up to that point. So this is why smoothing is a much better idea if real-time capability is not important. In smoothing, there are three different types of smoothing. I want to go through them as well. So that's called fixed point smoothing, a fixed lag smoothing, and a fixed interval smoothing. So that means, for example, if this is time 0 and this is until I have my measurements up to that point k here, that's what we had before, and I'm interested at my parameters at one fixed position time point, right? Then if I then recalculate this estimate at that time all over again, as long as my measurement grow, then I call this fixed point smoothing. Yeah. And then there's something called fixed lag smoothing. This is if I'm interested in my state at a certain time. So I have my measurements up to that point, and then I'm interested in my state at that time with a fixed window length here. Then I can they call it fixed lag smoothing. The last thing, and this is the thing where we're actually interested in, is fixed interval smoothing. So we have all measurements from here to here, and we want to know we want to estimate all states at all k's between 0 and t. So this is the example that we are talking about. So this is I'm driving through the city from here to here, take all my GPS, inertial measurements, laser scanners, and so on, and then later on in the post-processing step, calculate the best possible trajectory between here and here using all the measurements I have. So this is the one that we're interested in, and there are some examples also for those, but this is the main problem that we're trying to solve here. Okay, in order to explain what possibility we have, we look again at this Kalman filter here. So just to remind you the conventions, the notion, right? So this is the state. The estimated state is x. The estimated x with a minus here is a predicted state. Phi is a transition matrix. P is a covariance matrix. With a minus, it's a predicted covariance matrix. And Q is system noise. Okay, and these are the involved variables, and we now want to go through the technique of Kalman smoothing. One option for smoothing is the so-called forward-backward filter, and what it means is that if I have here my 0 and here my t that we've seen before, so I have measurements from 0 to t, and I'm here at time k, then I'm running one normal Kalman filter, which we call XF for forward, X forward, which uses all the measurements up to the time k. And I can also run in parallel, let's say, another Kalman filter, which we call XB, yeah, which runs backwards in time from here also to that position k. Yeah. So there are two filters, one forward filter from here to here and one forward filter from here to here. And the idea is if I now combine the estimates from the backward filter, one backward filter from here to here, if I now combine the backward filter estimate at that time with the forward filter estimate at that time, then this is something which uses all available measurements. How does it look like? So I have my new estimate. So this is now the smoothed estimate, and I combine it as a mixture of a forward filter and the backward filter estimate, right? So this means it's the estimate, and this here means predicted. This is the minus we've seen before. This is for the prediction. The reason that we use a predicted here and here we don't use a predicted is pretty simple, because if you are at that time k here, so this has a k, this has a k, this has a k, this and this. If we are at the time k here, then we have to use, we can't use the measurement at time tk twice. So here, coming from with the forward filter, this is the estimate after using the estimation, the measurement at time k. And in the backward filter, this here is the measurement before using the measurement at tk. So that ensures that we do not use the measurement at time k twice, because this wouldn't be wouldn't be valid because they have to be independent. You can now say that KF and KB have to sum up to 1. So the sum of K, so both parts have to be summed up to 1. So you could rewrite this a bit to this. So this only now incorporates the forward constant here, which says only the filter, the weighting factor for the forward filter. And if you now start the minimization process, right, you can this is expectation value of the covariance, and what we want to do is we want to minimize P, and if you minimize P, then the result is that KF is the predicted backward covariance divided by the forward covariance plus predicted backward covariance, and the factor for the backward estimate is according to this. Okay, and if you look at this, then this is basically basically a weighted mean of the forward filter and the backward filter. You can also calculate the covariance of this, and this is like written here. And this is also similar to a weighted mean. Okay, this is called a forward-backward filter. What we have to make sure is that the two filters which are combined here, they are completely independent. So what is not allowed is to go to the back and then start with the backward filter from the final estimate of the forward filter. So we have to start with an unknown position at the end and with an unknown infinite covariance at the end to make sure that both components are not depending on each other. And this is what you have to make sure. And yeah, so this is a so-called forward-backward filter. This summarizes the equations that I just showed. If you're interested in the details on the derivation of this forward-backward filter, you can look in the book from Dan Simon, which is called Optimal State Estimation. Here, the derivation of these equations are written in a very detailed manner. It's important to mention what you need to remember in order to do this filtering, right? So what you can see here is that you need the state for each. In order to calculate the smoothed estimate, you need all the states from the forward and backward filter, and you need all the covariances from the forward and backward filter, right? So you need to remember, you need to run the filter twice each time, also from forward and backward, each time remember all covariances in all states in order to calculate the new state. A bit more efficiently, this can be done in a Rauchtungs-Riebel-Smoother, which we will see next. The Rauchtungs-Riebel-Smoother is a more efficient way of doing a forward-backward filtering. And it's the one which is actually used in most cases, at least for GNSS IMU integration filters. So what we do here is we calculate first one one forward filtering algorithm. So we go through the through the normal Kalman filter and calculate it between 0 and t. And the second step, we go backward from t to 0. And then we do this. We have a new estimate, which is the forward filter. And we add the difference between the forward filter and the last smoothed filter with some sort of weighting matrix, with some weighting factor here. So again, this is xk, which is a smoothed estimate, and it uses the forward filter estimate. It uses the last smoothed estimate and the last forward filtered estimate. Yeah. So it's a recursive formulation. So it's not going from here to here and then from here to here and then mixing them up somehow, because it's a recursive thing. So we first go to the end, yeah, and then go step by step backward and update our smoothed version. So how does this A look like? The A depends on the forward covariance, depends on the phi matrix, and depends on the predicted covariance of the forward filter. Okay, and this is how it looks like. So the advantage here is clearly that you don't need to store all the covariances of a forward and a backward filter. You only need to store the covariances of the forward filter, and then going backwards through it, it's just a recursive formulation which only uses always the last smoothed estimate and the last predicted forward estimate. The result is actually equivalent to the forward backward filter, but it's a much more efficient algorithm. And this is an algorithm which is used usually in GNSS IMU integrations where smoothing can be applied, which is usually the case if you're not in real time. This summarizes the functions I derived, I've shown before, and again, I want to point out to that book by Simon, where you can have a more detailed look on it in the case you're interested. Okay, let's see what we have now. We have seen this plot here already. So the example was some trajectory here, then there is a GPS outage, and then the error. So here is the error, right? The error on the y-axis. The error grows over time, and when suddenly GPS is back, right? The filter jumps back to that direction, and that's it. So if we now do another calculation from the back, starting from here, right? Then the error, let's do that here, right? So this is my error again, GPS outage, and then I'm jumping back here to that direction. And now if I have a backward filter, it does the same the other way around, right? And here it jumps back. And if we combine it now, then this is basically what we see here with the blue line, right? So the actual error becomes smaller. So we have, of course, still the biggest error in the middle between those two outages, right? But the maximum error is much, much smaller than if we would go to the end. So this is what smoothing can do for us, right? So it improves the the final positional error, because we start from the back, and then all the errors here are reduced. So this is a very nice example how smoothing helps in the sense of GPS IMU integration. At that point now, I want to talk a little bit about how to evaluate the quality of the estimation. So we now just said that the smoother will make the error smaller. There will be some improvement, and at that point is a very good thing to talk about how we actually evaluate the quality of the estimation, or how do we actually evaluate the quality of a filtering algorithm or a system. And this is not a very simple, not a simple question to answer. What I want to hear is I want to discuss a little bit without providing a recipe for doing it. I just want to discuss different aspects on how to evaluate the quality of a trajectory estimation. The first thing you could do is you could look at the covariance. Yeah. So if you remember here the filtering equations, then you could look at the covariance of the estimate here to estimate the accuracy of your estimation. This is only okay if all models and all uncertainties are correct. So if all the models that I use here for R and for Q, if they are all correct, then this P gives you a good estimate about your estimation accuracy. But if you have systematic errors included, so for example, there are systematic errors in the measurement which are not modeled within the filter, then this covariance here usually is much better than in reality, than it is in reality. And this is a big problem in Kalman filters. If you look at these covariances, actually it's not only in Kalman filters, it's everywhere where you do some sort of adjustment on state estimation, then the covariance is only valid if all your assumptions that you put in are valid as well. You can see clearly here that the covariance does not depend on the measurements. So if all measurements are completely wrong, yeah, because the sensor is broken, then all your estimates at the end, all your xk's will be completely wrong as well, and your covariance will still look very nice, right? So this, don't just look at the covariance. This is what I want to say. It's also interesting to note that the covariance is not necessarily changing over time. It only changes if the Q here changes, right? Or if the Q is not changing, but the time frequency of updates is changing. Or it changes when the measurement noise changes. So in a situation where the process noise stays constant and the measurement noise as well, in this situation the covariance over time, right, is this P, will basically go like this and stays more or less constant. Yeah, this is the initialization time of the filter. So until here, then the filter converge, and then the covariance will be pretty similar. So, and still at the same time, the actual error of the estimation can be completely different, can be completely wrong, right? Okay, this is just to note that the covariance of the Kalman filter is not always, it's not always a parameter which you should look at to derive the quality of the estimate. Another good thing which helps is to look at the innovation. Yeah? So the innovation is the difference. This is innovation. The innovation is the difference of the actual measurement and the predicted measurement, right? So this basically says how your predicted state is consistent with the measurement that you actually do. And this is good hint. So if these values are always crazy high, then probably something's wrong with your prediction, right? Then your prediction is usually wrong. However, it is not clear if this distance here comes from wrong measurements or wrong predictions. So if there is a chance that your measurements also are wrong, yeah, because of outliers or whatever, then you don't really know where it comes from. It can be from a wrong prediction, or it can be from a wrong measurement. You have to consider this very carefully if you look at it, but it can give you, if you want to check if your filter is doing the right thing, or if you want to find errors or something, then it's a good trick to look at the innovation, and it's a very often forgotten methods to look at these things. Another thing which you could do to evaluate a filter is to look carefully at all estimated states. Usually you look, so if you write a filter for position and orientation estimation, usually what you do is you look at the position, output, and you think, oh, that looks nice. And then you think that your filter is actually working. But this can be completely wrong, right? So it could be, for example, that your process model, so your prediction step, your process model is completely wrong, but your measurements are so good that they basically override all the wrong predictions that you have done in each steps, right? So if you trust your measurement and your measurements are good, then the filter result can look nice. Yeah, you have the feeling that your filter is doing the right thing, but the implementation of the system model is still completely wrong. This is possible, right? So it's always a good idea to look at all states in order to evaluate what your filter is doing and if it's doing good. This is an example of biases. So I said before that in GPS IMU filters, integration filters, we usually model the bias of the accelerometer and the gyroscope. We know that they are not changing very fast, so we know that they are more or less constant over time. So if we see something like this here, very fast changing accelerometer biases, yeah, then this may an indicator that there's something wrong. Usually this means that there are differences between predicted measurements, the prediction and observation, which then are somehow absorbed by the accelerometer bias estimation. So this is a good indicator if this is what's happening. So the bias is not at some point being constant like here, right? So this is very nice, right? So it in the beginning it's somehow wrong, and then it converges to constant values. So this means everything is fine, or it's an indicator that things are going well, and this here might be an indicator that they are not. Yeah. What I want to say is it's very good to look at all estimated state and not just at the position, because this can lead to the wrong assumption that your filter is doing good, but it is actually not. So what is another thing? If we not only want to look at the filter, the best thing we probably can do is compare our result with a reference solution. Of course, this is the best type of evaluation that you probably do, but there are several problems with it. The first thing is you need a synchronization between a reference system. So reference system means it tells me the true value, the true position, or the true orientation, and true means usually a factor of 10 better than the system that we estimate. So we need a synchronization between the reference and the estimation results. And this is a first thing. So maybe you have a system which is very good, but it doesn't give you the position values exactly at the same time that your system is measuring them. So then this is a problem. I will come to that in a minute again. The other thing is that a reference solution is usually difficult to realize in auto scenarios, right? So what is a good orientation reference system in an auto scenario? It's not easy to realize, especially especially in our case where we want to evaluate a high accuracy IMU measurement system and a high accurate GPS measurement system. To evaluate this is very difficult because there are not many systems which are actually better than that, than the sensor that we use anyway in the system to evaluate, right? And the other thing is how to parameterize the error. So if this is now the error over time, so what do you say now is the accuracy of the system? Of course, you can build the mean error, or you can build the root mean square error, but still, it's maybe you're interested in the maximum error. It's clearly an error which is not normally distributed. Yeah, so it's a bit difficult to say what accuracy is important. The other thing is, depending on the filter tuning, it could be that there are that for example the estimated trajectory is following the true trajectory a bit it's a bit smoother, right? But it's following with a time lag, which might be, depending on your application, completely fine. But it's maybe not what you want to put into a specific accuracy parameter value. So the question is, how do you now generate a number from these differences? Coming back to the reference system, I want to put some examples here. What is actually done? So this is a tracking system which is usually used indoor for robotic applications. It's a system which is based on a vision-based tracking system, high data rate, high accuracy for orientation and position, and it would provide a nice reference setup for our systems that we have, but it's a very close volume where it works, and usually it only works indoors. So for some applications, this is a very nice thing. For applications which are in the outdoor area, it's not really. In the outdoor area, this is an example what we realized at our research campus in Klein-Altendorf. Is a trajectory, like a roller coaster trajectory here, like a train, and what we can do, we can let our system run on that track here as a reference trajectory, and then compare with our estimated trajectory. It gives us basically a reference trajectory for the system. We could use RTK GNSS for as a reference position, but again, if the RTK GNSS is also what we put in as a measurement observation device, then it can't at the same time be our reference position. And another thing which we could do is use a total station, as shown in this example here. This is a total station. There's a prism here, and then you could use this for tracking the thing as a reference trajectory. Here, the biggest problem is the time synchronization, because time synchronization between total station and the estimate of the system is not a trivial task. We will talk about it in some of the future courses. The last thing I want to mention here, how to evaluate the quality of the estimation, is an indirect evaluation. So if we have these these targets here, where the point in the middle has a known coordinate, yeah, then our georeferencing equation of our laser scanner will create the same, so like a point cloud of that target within world coordinates. And if we know now these in the world coordinates, then we can compare the position here created by our mobile laser scanning system and compare it with a known position in the real world. This is a nice thing, and it feels like the best thing we can do, but you have to be aware that, of course, this includes the trajectory parameters here, right? So the position of that target here includes the trajectory parameters, but it also includes the measurement of the laser scan and the calibration. So all scanner errors and all calibration errors will end up in the difference as well. So there are other, it's not just a trajectory here which we are evaluating, we're evaluating basically the whole system in total. We've done that with our system that we have using these methods, and we can see that the positional deviation of multiple targets and multiple runs is very small. It's in the with a standard deviation below a centimeter, so that's a pretty good thing. But still, we don't know exactly what of these deviations come from the trajectory estimation and what comes from the calibration error and what comes from the center observation. Let's now discuss these methods of comparing different trajectories, especially focusing on the example of smoothing, which we've seen before. So here, this is our compass, and this is our mobile laser scanning system, which we've seen a few times already. And what we did here is we drove. This is the library, yeah, and we drove here towards. I think this is towards Poppelsdorf, here along that, then back here, in between the new buildings on the campus and towards here. So this is the trajectory that we drove with the system, and it generated measurements from the IMU is here, like angular rate and accelerometers, and the GPS coming from here. So first, let's have a look at a calculation which is only using strap down. So this is the no GPS, no odometer, nothing. It's simply integrating GPS and IMU observations as we've seen in the beginning as repetition of the last semester's course. We started, however, with known position and known orientation. And here you can see that this, for a long time, works really nice, and here it starts to drift away, right? So it's actually not too bad, but here it starts becoming worse and worse and worse, as we've seen before. You can still somehow see that the form of the trajectory is similar, but there are drifts in between. If you use a very low-cost IMU, this is done with a very high-grade IMU. If this would be done with a low-cost IMU, I think you would not even, in the first like seconds or 20, 30 seconds, the position would just go away somewhere here, right? So that it's still is visible within that boundaries here for the whole track, tells you already that this is a very, very good IMU. Another interesting thing is that if you add an odometer measurement, but still no GPS, right? Just add the odometer to the strap-down integration, which just uses, this is now a Kalman filter with a strap-down integration as system model and odometry measurement as odometry observation as measurement. This already let the whole thing look much, much better. And this doesn't have any GPS included, right? It just tells you how nice an odometer can help in improving the estimation. What we do here is we compare with GPS, right? So the green dots here are an RTK GNSS observations with an accuracy of a few centimeters, let's say, depending on where you are on the trajectory. And this is, of course, a valid reference system if it comes to evaluate odometer plus a strap down or strap down only trajectories, because it is basically an independent system which is not used in the actual estimation of the trajectory. It just gives you the reference in this case. So that's pretty nice. The quality of the GNSS receiver is seen here, is written here, right? Because we will use GNSS now in the next slides. We want to have a look at the quality before. So how do you elevate the quality of GNSS? That's a bit difficult, as you already know, hopefully from the last semester. So one indicator is the number of visible satellites. So here we see about 20 satellites, yeah. And here is an area where we go far below 10 satellites, yeah. And this is in the area within the buildings on the new campus, where most of the satellites are blocked. Yeah, and these areas here we artificially introduced areas of no GPS, right? So we deleted all satellite observations in this area here in order to estimate, to evaluate the performance of the smoother. This here is a standard deviation of the GPS as it comes out of the receiver. So the receiver calculates a position and gives us some sort of covariance or some estimation accuracy. We don't really know how the receiver manufacturer calculate this, but it of course also is a good indicator on what's going on. And you can see that when you have not so many satellites here and probably a lot of multipass and other problems within the area between the buildings, then the estimation accuracy goes from here, this is probably centimeters, right? Goes up to 5 to 10 meters. Yeah. And this is in that specific area between the buildings. Good. So what do we have now? We compare different tracks. We compare a normal Kalman filter, right? This is a smoother. It's an RTS, Rauchtumsriebelsmoother. This is GPS, and there are areas which I will mark with a pen later, where we introduce the GNSS outage. This is here and here. It's an artificially introduced outage of GPS. So here. And of course, now it is difficult to use the GNSS as a reference, because the GNSS is also used in the filter. The only places where we can somehow use it as a reference a little bit is in those areas where we actually not use it, right? So here we introduce an artificial GPS outage, and of course we can compare with the GPS that we have at that time to have some sort of reference. Okay, what we do, we look at, as I just said, we look at the difference to GNSS data, although this is not the perfect way of reference, but this is the only chance that we have. And we look specifically at three different points. So this here is area 1, right, where we can see here that we see the behavior exactly as we discussed before in the smoothing part, right? So this here is the error going bigger and bigger, and then it jumps back to 0 after the GNSS outage, and the same here for the noise component, right? It goes bigger, and then jumps back. And in the height component, apparently this wasn't a big problem. It only was drifting away for east and north components. The third area here is not a GPS outage at all, but it's that area that we mentioned before where the GPS positions are very, very bad. And if we look at this here, then we see that the difference between GNSS data and IMU data are going up to 3 meters, yeah, or 2 meters here. And the interesting thing to note here is that why we know that the difference here is coming from the filtering estimate. We know that here in this area the filter estimate is probably much better than the raw GPS, than the GPS positioning. So these deviations here come from the GPS and not from the estimated filter position. Let's go a bit more into detail in these areas. So we're coming from here, right? Here the GPS outage starts, and you see that the normal Kalman filter is drifting away from the smoother, and it's drifting away from the GPS measurements. And at some point here, when the GPS comes back, it jumps back to the true track and continues, right? So here we can see this behavior of drifting away and then jump back, and we can also see that the smoothed estimate, the red one here, because it does the same thing, it calculates the same thing from the other side, right? Doesn't have that behavior. So smoother will get rid of those jumps that we have here. And we have a similar behavior here at the corner. Here it's not that problematic, but it's still there, right? We can see here that the blue one is going away. So this is the motion direction here, and then it jumps back, and the red one doesn't haven't that issue, right? The third area, it's an interesting area, because what we see here is that the green dots, right, the GPS observations are now being a bit crazy, right? And this is what we've seen before, that in this area we are between the houses, the buildings. There will be many multipaths, a lot of obstructions of signals and these things, so that all these observations here from the GPS receiver are basically systematically wrong. And if you now look at the blue line, this is the normal Kalman filter. Yeah, it also uses as a measurement noise the GPS standard deviations that it gets from the receiver. And what you see is that it basically not really is listening to the GPS anymore, right? It's because the standard deviations for those measurements here are so high that they are basically, that these observations are basically ignored until that point. When GPS observation noises or position noises from the receiver are very small again, and then we have this jump. So it's very similar to the case of having a GPS outage, but the outage is not artificially introduced by us. The outage is given basically by the fact that GPS noise matrices noise values are very high. And we can also see that the smoother now is not having those problems. So I would consider the smoothed version as the most accurate version here. And it can be used very nicely also to see what systematic deviations you get in GNSS measurements. So you can see that all the measurements here are basically, all the GPS measurements here are systematically shifted by a few meters, right, to one direction. And this is a very critical problem in Kalman filtering if you have like systematic errors in the absolute measurement system. Just to again show the thing, what we've seen before, we look at the bias estimations now, and we can see that the bias is nicely converging to a certain point and staying there roughly. This is pretty similar. So this basically tells us something about the health of our filter, and that it's kind of doing what it's supposed to do. Okay, let's summarize what you have learned today. So we repeated some of the points from the last semester on how position orientation can be calculated using inertial sensors and GNSS. We focused also on the fact how GNSS and inertial sensors are combined using filtering algorithms like the Kalman filter. We talked how inertial sensor errors influence the estimation. This means so how fast do they grow, and where do these errors come from? And we said how smoothing can help to get rid of those errors, particularly the errors which come from inertial sensor strapped-on integration. So what is the difference between filtering and smoothing? When can we do smoothing? When can we do filtering? And when and why smoothing is better? We learned what the RTS smoother is. So this is some sort of standard technique which is often used and which you will also implement in one of the exercises. And then we discussed a little bit how you can evaluate the quality of the trajectory estimation. And how good does your filter perform? How good is your estimation result? And these are the things that you should take home from the lecture today. With that, I want to thank you and see you next time.